Students, we know that all crystalline solids have three-dimensional structure, right? That means the arrangement of the constituent particles in any crystalline solid is three-dimensional. See, during the formation of this crystalline solid, the constituent particles of that crystalline solid, they pack as closely as possible so that the density of the crystal increases, thereby stability also increases. In this session, let us learn how the constituent particles pack each other and to form three-dimensional structure. Before understanding the packing of the constituent particles in three-dimensional structure, we should know about the arrangement of the constituent particles in 1 dimension, 2 dimensions, and 3 dimensions. First, let us see the close packing or the packing of the constituent particles in 1 dimension. See, this is how the constituent particles arrange in 1 dimension. Each constituent particle has 2 neighboring particles, right? If you consider this constituent particle, see, it is surrounded by 2 neighboring particles. In close packing, the number of nearest neighboring particles are called coordination numbers. Let me repeat. In close packing, the number of nearest neighboring particles are called coordination numbers. Now, if you consider this constituent particle, it is surrounded by 2 other particles, right? Or it has 2 nearest neighboring particles. Therefore, the coordination number of this particle is 2. Same way for other particles. Then you may ask, what about these 2 particles? Here the coordination number of this particle is 1? No. See, students, in close packing or in any crystalline solid structure, we don't consider the particles present at the surface. See, these 2 particles are present at the surface, right? So, we don't consider the particles present at the surface. In 1 dimension close packing, each sphere is in contact with 2 of its neighboring particles. The number of nearest neighbors of a particle is called coordination number. In 1 dimensional close packing, coordination number is 2. Now let us see close packing in 2 dimensions. Before arranging the particles in 2 dimension, first let us arrange the particles in 1 dimension. See, this is 1 dimensional arrangement, right? Now let us place the particles exactly below the particles present in this 1 dimension. That means like this. When we arrange the particles like this in 2 dimension, each particle is surrounded by 1, 2, 3, and 4 particles, right? In 2-dimensional packing, each particle is surrounded by 4 other particles. Now, in this 2-dimensional arrangement, is there any other way of arranging the particles? Here we have arranged the particles one below the other, right? Say, for example, this line is denoted as A, then this is also A, this is also A, isn't it? That means this is AAA type arrangement. Now, is there any other way of arranging the particles in 2 dimension? Let us see now. Again, let us have the arrangement of particles in 1 dimension. Now, let us arrange the particles below the depression of the first layer. See, in second layer, let us arrange the particles exactly below the depression. This is called depression. Just below the depression of the first layer. When we arrange like this, each particle in this arrangement is surrounded by 6 other particles, isn't it? Here, if the first layer is denoted as A, then second layer will be B. if first line is denoted as A, then second line will be B, third line again A, and fourth line again B, isn't it? Then we can call it as AB, AB, AB type arrangement. Yes. Students, this arrangement is called two-dimensional square close packing. This is called two-dimensional square close packing. And this is called two-dimensional hexagonal close packing. This is called two-dimensional hexagonal close packing. In two-dimensional square close packing, coordination number equals to 4 because each particle is surrounded by 4 neighboring particles. What would be the coordination number of two-dimensional hexagonal close packing? Yes, here the coordination number is 6 because each particle is surrounded by 6 other particles. In two-dimensional square close packing, the arrangement is AA type, whereas in two-dimensional hexagonal close packing, the arrangement is AB type. Now let us see the close packing in 3 dimensions. First, let us see 3-dimensional close packing from 2-dimensional square close packed layer. In order to make this structure 3-dimensional, first let us have 2-dimensional structures. In 2-dimensional structures, we have seen 2 types, right? The one is square close packing, the other one is hexagonal close packing. So first let us keep that square close packed layer first. See, this is 2-dimensional square close packing and this is layer 1, first layer. Now if we keep on placing the particles exactly above the particles present in the first layer, then structure looks like this, right? It forms simple cubic structure. So this is 3-dimensional close packing from 2-dimensional square close packing or 2-dimensional square closed packed layer. Now let us see close packing in 3 dimensions. In that, 3-dimensional close packing from 2-dimensional hexagonal close packed layers. See, this is 2-dimensional hexagonal closed packed layers, right? First, let us place the particles in the second layer in such a way it closes these spaces. When we arrange like this, see, we already placed one particle here, right? It has closed the space present between these 3 particles of the first layer. When we arrange like this, you know what happens? See, when we arrange or when we close this space present between these three particles, it creates a kind of space, or we call it as void between these 4 particles, and this void or that space is called tetrahedral void. Void means a kind of space. This space is called tetrahedral void. You know what is the significance of this tetrahedral void? If the crystalline solid is ionic crystal, then these particles are similar to anions, and inside this void, that means space, cations will be present, because cations are smaller in size, anions are bigger in size, and these particles are something analogous to anions. That means anions form the crystal lattice and cations will be present in the voids. In a crystal, number of particles equals to n, then number of tetrahedral voids will be number of tetrahedral voids equals to 2n. That means the number of tetrahedral voids will be twice the number of particles present in the crystal. Now let us place the particles in this second layer. When we place these particles in second layer, it looks like this. Suppose the arrangement of the first layer is A, then the second layer is different from the first layer, right? Therefore, can we denote this as B? When we arrange like this, see, this arrangement creates a space here, correct? Or we can say void, and this type of voids are called octahedral voids. In any crystalline solid, the number of octahedral voids are equal to the number of particles. Say for example, if there are n number of particles equals to n, then number of octahedral voids also equals to n. When we arrange the third layer exactly like first layer, then the arrangement is like this, and this arrangement becomes ABA type, ABAB. When it is ABAB type arrangement, then it is called hexagonal close packing. Then it is called hexagonal close packing. This hexagonal close packing also we can call it as HCP. When the arrangement of the particles is HCP or hexagonal close packing, the packing efficiency will be highest. If the packing efficiency is highest means the coordination number also should be more, right? Because what is coordination number? The number of nearest neighboring particles. So if there are more number of nearest neighboring particles, then that crystalline solid has very closely packed structure. So in HCP, the coordination number of the constituent particles will be 12. Instead of arranging like this, ABAB, we can arrange the third layer like this. See, when we arrange the third layer like this, it is different from both layer A and layer B. Then if we place the particles like this, the arrangement will become A, B, C, A, B, C. When the arrangement is ABC, ABC type, then that arrangement is called cubic close packing. Or we can call it as CCP. Even in the cubic close packing, the packing efficiency will be highest. That means here also the coordination number is more. The coordination number in cubic close packing equals to 12. Here also it is 12. So now we have two types of three-dimensional arrangement. The one is hexagonal close packing or HCP, or cubic close packing, also call it as CCP. Whether it is HCP or CCP, in both the arrangements, the packing efficiency is highest and the coordination number is 12. When the arrangement is cubic close packing or CCP, by default it forms FCC arrangement. If the arrangement is cubic close packing, then it forms FCC arrangement. Students, I hope this is clear to you.